Okay, hello everyone. Let's pick up where we left off last time. So, benzene, let's go. So, we went over that N2O example, a lot of Lewis structures, a lot of resin structures. It's important that we know how to draw these, and we just don't draw anything for the resin structure or for the Lewis structure without first evaluating what we have drawn, okay? All right. So, let's look at this next example. Say we have benzene, a very notorious chemical compound, very popular solvent, is a carcinogen. We really can't work with it anymore unless we have to. It's like a blight on any chemical paper that you publish. You don't want to use benzene unless you have to. Now, ironically, in gasoline, there's toluene, which is basically benzene with a CH3 group attached at one of the carbon atoms. That, however, has the toxicity around that is severely, I won't say severely, but very different from benzene. It's not as toxic as benzene, so that's why we put it in our gasoline. But it still smells awful. That gasoline smell, most of it is because of benzene. Sorry, not benzene, toluene. And if we don't have to use toluene, we don't want to. And that's because toluene just has that characteristic kind of foul odor. It's not foul like a fart or like a very unpleasant smell. It's just still unpleasant to be around. And if you actually happen to smell gasoline just by being near it, you can see why it's not that pleasant. Okay, and it has to do with this benzene group. Smells have an interesting way of how it gets registered. Our noses are like our own type of spectrometer for detecting different kinds of compounds. So it's an interesting thing. The olfactory, I think I said it right. I probably said it wrong. It's an interesting kind of process, I would say. All right. Anyway, so the structure of benzene is actually what gives resonance its popularity, or its fame in chemistry, and that's because back in the day where chemists still didn't have access to instruments, they had trouble. Well, I wouldn't say they had access, but it was very difficult to determine the structure of compounds. And one chemical that puzzled them for many years is benzene, because it has the best known resin structure in chemistry. We based our discussion of resins around benzene, and that's because the benzene, motif is present in a lot of different compounds. It's like one of the main motifs in many natural products. Okay, so we can arrange. So benzene is C6H6. That's the molecular formula for benzene. So let's arrange the 6 carbon atoms in a ring and draw 2 resins Lewis structures for benzene. Okay. So one of the things we have to keep in mind, all the carbon-carbon bonds in benzene have the same bond length. Okay? So we got to think about, okay, let's draw all these benzene atoms, or these carbon atoms. Another thing we have to think about is ethane has a carbon-carbon bond length of 154 picometers, and ethylene has a carbon-carbon bond length of 133 picometers. However, benzene has a carbon-carbon bond length of 139 picometers, but all the bonds are the same. So what does that mean? We can't draw a benzene. So let's think of things we can draw, right? We can't draw. So let's arrange the benzene in a ring. So C, 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 and C. So naturally, we would arrange this in a hexagon, and we could combine it like this. Okay. So if this was the case, right? Maybe I should move this over a bit so we have room to draw. Okay. So naturally, if we do that, right, now we have to say, okay, we have 6 hydrogen atoms, but where are we going to put them? There's only 6 carbon atoms, and if we only put hydrogen atoms on 1 carbon, there's going to be a lack of an octet, right? So, but if we think about our usual way of drawing Lewis structures, we have 6 times 4 valence electrons for carbon, okay, plus 6 times 1 electron for hydrogen. Okay, so we add those two, we get a total of 24 plus 6 dirty electrons for benzene. All right, so we already drew 6 single bonds, so that's 12 electrons. So we can only draw 6 more bonds we could draw 9 bonds, right? So how are we going to draw 9 bonds, but we only have 6 hydrogen atoms? So first, let's put the hydrogen atoms on each carbon, because that makes the most sense, right? Because if we add both hydrogens onto the same carbon atom, we'll run into a situation where we have a carbon atom without a hydrogen, and that doesn't make much sense if all the bonds around carbon, all the carbon-carbon bonds in the benzene molecule, it won't make sense if they're all the same. So let's write hydrogen here, hydrogen there. Like so. Okay? So that's our structure here. Now, so what does this mean? We have 12 bonds. That's only 24. We need to draw 3 more bonds. And we need to draw them in such a way that makes all the carbon atoms have an octet. Okay? So if we put a bond here, so the key to this one is that we alternate the double and single bonds in the ring between the carbon atoms. Because if we put a double bond here, right, this one makes sense because now one carbon atom now has 5 bonds to it. 2 from each double bond, 4, and then 1 bond from the hydrogen, so that makes 5 bonds. So that's not possible because a carbon can't expand its octet, right? It's in period 2. So we can alternate the bonds here. Like that. So now every carbon atom has an octet. So that's how the structure of benzene was proposed. And it gave people conundrums because if you were to analyze benzene, it only gives you, if you were to do some experiments on it, you'll figure out that the data presented gave some insight that it was symmetrical, and this was the way we solved the structure of benzene, because the fact that it only gives you 1 single length for all the carbon atoms is because of resonance. So remember how we said resonance can alternate between single and double bonds, and that will make the length intermediate in between a single and a double bond. The same case for here. Same case for this molecule. We can move the electrons around in the ring, and you see that when we draw the other resonance structure, that the bonds migrate here like so. And you see that each carbon atom now, so let me just redraw these carbon atoms. Each carbon atom now has both single bond character and double bond character. So each carbon-carbon bond will alternate between being a single and a double bond. And what happens then is that these bonds are going to be intermediate in length of a single and a double bond, and that's what we see for 1 during 9 picometers. Okay? So let's answer this question. So why is the carbon-carbon bond length in benzene less than that of ethane, but greater than that of ethylene? So we can say because of resonance, okay, the CC bond length, the CC bonds not carbon, in benzene have both single bond and double bond character. So it's intermediate between those two types of bonds, and that's why we see a longer bond length than a typical CC double bond, but a shorter bond length than a typical CC single bond. So that's the kind of answer you would put if I asked that question. Okay. There we go. So benzene is the classic example of resin structures. So if benzene didn't have resin structures, okay? So if we had the similar type of molecule to benzene, but it didn't have the ability to write two equivalent resin structures, then not all of the carbon-carbon bonds would be the same. And the fact that there is resonance gives us info that benzene the structure of benzene is a mixture or an average of hybrid of these two Lewis structures. Okay, so let's go on here. Let's move on. All right, so now let's talk about partial charges and covalent bonds. Okay, so let's classify the bonds in nitrogen monoxide and the oxygen elemental oxygen in the atmosphere as either covalent or polar covalent. Okay. So when we draw these bonds, so remember NO. So NO we have 5 electrons for nitrogen and 6 electrons for oxygen. So we have 11 electrons here. Okay. So we could draw a few structures here, but let's draw the nitrogen molecule. No. Okay. So this is an odd number of electrons. So you'll have this in some cases. So it might be better to put an octet on oxygen just because it makes sure that the most electronegative element has the octet, which kind of makes sense because it would want to hog all the electrons to itself because it's more electronegative. But now we see here, we can actually draw a few resin structures here where we rearrange the electrons here around nitrogen now. Like that. Okay, so in either case, they look pretty. They don't look too happy, and that explains why some of these radicals they are very reactive because they lack an octet of electrons, so they're electron deficient. But another thing we can do is let's see. So we drew the formal charges here. Now, in this case, they would flip here. No, so it actually becomes worse. 2 minus and 2 plus. So that's not a very good resin structure. So we don't want to draw it like that. We can also draw it like this. Okay, so it almost has an octet now. So this will be, no, this is the better structure. It's actually neutral now. Both of these are neutral. But you see here, no matter what we do, one atom will not have a full octet because of the odd number of electrons. Okay? And if we switched it around here, we have the nitrogen have the double bond instead of the oxygen. This 1, 2, 3, 4, 5, 6. This will have -1, and this will be +1. So it looks like this structure, when the octets on the nitrogen, these are the best. So that's one we would go for. Okay, so how do we classify these bonds as covalent, as either covalent or polar covalent? Well, let's look at the electronegativities. So oxygen has a higher electronegativity than nitrogen, so we say that this bond is polarized, partially negative on the oxygen, based on oxygen having a higher electronegativity. It'll pull electrons towards itself, and so it'll have a partially negative charge. Nitrogen, on the other hand, is electron deficient because of that, so it'll be partially positive, like that. So we say these are polar covalent bonds because you have a partial charge difference between the two atoms. And this is due to difference and so En means electronegativity. Difference electronegativity between, so let's write between instead. Nitrogen and oxygen. Okay? Like so. Alright, now let's talk about the oxygen-oxygen bond. So, dioxygen. So in this case, we have 2 oxygens, so we should have 2 times 6 electrons for a total of 12 electrons. Okay. So, if we try to balance these electrons, we can write the form in 2 ways. 1, 2, 3, 4, 5. Like so. So like this. So we have a diradical. So now we have 2, 4, 6, 8, 10, 12 electrons as part of the whole system. Now, this is what we call triplet oxygen. So this is actually the most stable form of oxygen. And that might sound surprising, but the fact that there's 2 unpaired electrons on adjacent oxygen atoms is actually a stabilizing force because it can actually, they can actually spin pair between different orbitals on oxygen, and that causes triplet oxygen to be the ground state or the most stable form of oxygen in our atmosphere. So now we could draw a resin structure where we show that both oxygen atoms have a double bond between them. So you may think, okay, this should be the most stable form of oxygen. However, it is not. This is singlet oxygen, like I said before. The term singlet and triplet, it refers to how many unpaired electrons you have. So when you have no unpaired electrons, that's a singlet state. And when you have one unpaired electron, it's called a doublet state. I could go into why is that, but now's not the time to go into that. You'll probably go into that. You'll probably talk about spin states if you ever go to higher classes of chemistry. But you may see it also in if you take inorganic chemistry. But this is technically inorganic chemistry, but it's a little too advanced to talk about it here. You may talk about it in Chem 401 though. So if we have two unpaired electrons in our compound or system, that's called a triplet state. So this will be triplet oxygen because the two unpaired electrons are on different atoms and not paired. So this is actually triplet oxygen is actually ground state oxygen, and it's what we. So when oxygen interacts with other molecules, it's actually getting excited to a different form of oxygen. Well, in most cases, like triplet oxygen reacts and it generates singlet oxygen, which is what we call a reactive oxygen species, or ROS. And what ROS species like to do is they like to trigger something called apoptosis in cells, which is basically engineered or programmed cell death. So your body can generate ROS species to trigger cell death in response to a foreign invader, stuff like that. So there's lots of developments for medications that can cause oxygen to generate singlet oxygen species and ROS, reactive oxygen species, to destroy like cancer cells. Because if we can trigger a reaction in the body that only targets this specific type of cell or affects a specific area that's infected by cancer, we can battle cancer without having to use chemotherapy and stuff like that. Oops, this is don't want to go to sleep yet. Okay, so that's just the difference. Just the different structure causes the reactivity of this compound oxygen to be very different. Okay. So either way, we could draw these two structures. If you draw either one, it doesn't matter. They're both valid, okay? And you see here, the oxygen here, when we have a bond that has the same elements, our difference in electronegativity becomes 0, right? So because oxygen has the same electronegativity value as another oxygen atom, so delta electronegative, our difference here is 0. So what happens then is that we classify this as a covalent bond. So the electrons are equally shared. So this will be a covalent bond. So what this means is you have an equal sharing of electrons. Like that. Okay, so let's end this video here and we'll pick up in the next video on talking more about where these partial charges come from. Okay, so I'll see everyone in the next video.